With this video, we're going to go through the entire lesson of these real-life logarithms and exponential equations that we can solve. So it's going to be a little bit of a lengthy one, but everything that we're going to be dealing with just about today is going to be just a real-life application of these types of equations that we can solve. So we're going to use these equations to help us solve real-life scenarios, real-life equations. But first, what we need to do is get a little bit of refresher. At this point, you should be able to know how to do these types of problems. These are exponential equation problems. So I'd like you to pause the video right now. I'd like you to work out both of these problems. After you've obtained your answers, come back and push play. Check your answers here. If you're unsure how to do these types of problems, you probably need to go back in and watch the other video that I've got on solving logarithm equations or exponential equations. Long story short is we're going to have to take the log of both sides. Then using our laws of logarithms, we move this exponent out in front. Okay, and then we divide both sides by that. Again, if you're not quite 100% sure how to do those, go back and watch another video. Let's try one more practice here, then we'll get on to some other things. So go ahead and push pause on the video now. After you've obtained your answer, come back and push play. Check your answers here. Okay, so right now we're going to take this knowledge here and start applying it toward a real-life scenario. So here's our real-life scenario. You invested $10,000 at the age of 16 with 14% interest is going to be your return rate, and it's compounded continuously. How many years will it take for your money to triple? Okay, these are going to be key components of what we're going to do. Triple, we have to know what triple means. Triple would mean 3 times as much as our original amount. So if our original amount was $10,000, triple would be $30,000. Okay, that's going to be key. All right, so let's look at this one. It's going to be, here's our original compounded continuously interest equation. Compound interest, but it's continuously compounding. Okay, so we know what A is in this case. A is going to be our triple amount, and triple is going to be $30,000. P, this is the amount we initially started with. This is $10,000. E is the number E. Interest rate is 14%. Remember, it's 0.14. T is what we're looking for. We don't know what time is, so that's what the whole purpose of the equation is to determine. Okay, in order to do this one, what we're going to do is we're going to have to find out what T is. So we've got to get T all by itself. Well, it's in an exponent, which means we're going to have to take some logarithms of it and everything. But first, what we need to do is try to isolate this E raised to the 0.14 times T. So I need to get rid of this 10,000. So what I'm going to do is divide both sides by 10,000. In doing so, 30,000 divided by 10,000 is going to give me just plain old 3. 10,000 divided by 10,000 is 1. That leaves me with just E. Perfect. Now that we've done that, we can take the logarithm of both sides, and we can do either one, log base 10 or natural log. Natural log is going to be 1,000 times easier. The reason is because we have this number E. Remember, the natural log is a base E. So that's going to help cancel it out. We'll kind of go through that in a little bit. But again, you could use either one. I highly recommend you use the natural logarithm, though. So I'm going to take the ln of both sides. So all I did is add an ln to both sides. Remember, when we're doing this, we haven't changed the value at all because we're doing it to both sides. Okay, well, a neat thing occurs at ln e. This is essentially the natural log, or log base e, of e. What happens is those two cancel out. So when those two cancel out, that leaves me with just 0.14t. That's it. So that's why it makes it a lot easier if you use the natural log. Now, you can, if you want to, if that's confusing to you to do this, what you can do is move this 0.14t to the front here using our rules, our laws of logarithms. We can move that one to the front. But do me a favor before you do that. Let's just type this in. ln e. If you type that into your calculator, it's just going to give you 1. So by the time we move this 0.14t to the front, then we're going to multiply it by 1. That just gives us 0.14t. Okay, well, now that we have that, what we're going to do next is we're going to plug this ln3 on the left-hand side to our calculator. So just take out your calculator and you'll plug in ln3. Hit enter. See what that gives you. You're going to need to round it at some point. This one asks you to round it to the nearest thousandth. You do not want to round to the nearest thousandth yet, only in your answer. So you want to give yourself a couple decimals. Usually I try to go a couple of decimals past whatever that is. All right, well, now that we have this, we're just looking to solve t. This is 0.14 times t, so I'm going to divide both sides by 0.14. Once I do that, I find out that it's 7.847 years. Okay, so in 7.847 years, my money will triple if I receive a rate of return of 14%. When you are entering this one into the online system on the computer, just type in 7.847. Don't type in the label. But 7.847 will work just fine. All right, now I want you to try this one. This one is almost identical to the previous problem that we just did. A little bit different numbers, percents, that type of thing. But go ahead and try this one now. Push pause on the video. Then once you work it all out, you come up with your solution. Come back in and press play. Check your answers. Okay, again, we have to round to the nearest thousand, so this should be 5.776. Again, if you're going to type it in online, we're not going to leave the label there, but that will work just perfect. Okay, now I've got two here, and one builds off the other, so you got to do this one first, okay? Do this one up here, and then after that, this will be number 2. So push pause on the video now. After you've obtained your answer, come back and push play. Hopefully you identified that this one was really similar to the one that we just did. The only difference is we know what the years are. At 20 you have this amount, at 30 you have this amount. So we know what the years are. The years would be 10. The difference between 20 to 30 would be our 10. What we're looking for here is the rate. So we're actually solving it for the rate. We're going to use the exact same process. We're just solving for r instead of t now, that's all. Well, now that we have that, how old will you be when your money triples? Okay, so we have to use this rate here to plug in over here. Okay, and then we can solve it for t. That's the one we were just doing. But you've got to know the rate here, and you don't know the rate until you can do number 1. All right, let's try this one. This one's going to be really similar to the one that we just did. So push pause on the video now. After you've obtained your answer, come back and push play at that time. Check your answers. All right. Now we're going to move on just a little bit here. And we're going to get into an exponential growth model. And this is population, initial size of the population, relative growth, time. This looks like a very, very brand new equation. Really, it's not. This is almost identical to the equation that we've been using for compound interest. Compound interest had one here, and then it just had an A over here, and it had a P here. Other than that, everything else is the same. We're just calling them two different things here, that's all. Instead of dealing with money, we're dealing with a population. But it's really just the same equation. This is the amount we start with. N of O is our, the initial size. This is the amount we start with. N of T is how much we end up with at the end. Everything else is the same. Growth rate, instead of rate of return, is just a growth rate. Time is still time. So it should feel similar to the equation that we were just using for compound interest. All right, well, let's see where we can actually apply this. Okay, so we've got bacteria here, and here's the model. T is measured in hours in this case. Okay, sometimes it's years, sometimes it's hours. You have to kind of look and see what the problem states. Now this one, it's hours. So here we go. What is the initial number of bacteria? So how many did we start with? Well, if we look up here at our function, we started with 500. So 500 should be your initial amount of bacteria. The growth rate on this one, well, the growth rate should be, and hopefully you should be looking at this and you're not saying that it's 4.5%. This one should be 45%. It's a very, very large growth rate. And bacteria usually has a lot larger growth rate than like an investment or something. So 45% is the growth rate on this one. How many hours, after how many hours? Ugh. How many bacteria exist after 3 hours? Okay, so all I'm going to do is I'm going to take this function up here, and instead of writing t, I'm going to write 3 and plug that one into your calculator. So I do that now. It should look just like this on your calculator. I plug in 3 and my answer should be that. Now this one I ended up rounding to the nearest 2 decimals, and that's fine. I didn't specify up here, but that's pretty much all we're going to be doing with this one. All right, so now let's get some practice on this. Mesa had 290,000 and change population in 1990. In 2010, the population was almost 500,000. So we're asked to find a function that models the population t years after 1990. So what we're looking for here is we're trying to find the rate. As soon as we can find the rate, then we can create this function. All right, well, we have to know the initial population and the ending population. We know both of those right here. Okay, so we're going to start plugging in some information. This is our ending population. This is in 2010. We had 489,253, so that's my ending population. Well, my starting population would be this, 290,811. And we know what the t is in this case. T would be the number of years from 1990, excuse me, to 2010, which would be 20 years. So T would be 20. Now what we're going to do is we're going to solve this equation for R. That's what we're trying to find. So we're going to solve this one just like we were solving our other problems that we previously did with our compound interest. Okay, so first thing that we have to do is isolate this quantity here, this e raised to the r 20. So we're going to divide both sides by this amount, our initial amount, okay? Divide both sides by that, I end up with this 1.6824. And again, we want to try to keep it out. If it were me doing a problem and I'm not pressed for space, I'm probably going to go out about 5 or 6 decimals just to be on the safe side. All right, from here, I need to get this out from the exponent. So what I'm going to do is take the logarithm of both sides. But again, I'm going to take the natural logarithm of both sides because it's the number e. And the natural logarithm has a base of e. Okay, so I take the natural log of both sides. When I do that, this ln and e will actually cancel. Okay, leaving me with just whatever was in the exponent, in this case 20r. All right, now you'll notice here that I kind of switched these two around. We're used to seeing 20r written that way. We're not used to seeing r20. Both ways are correct. Not one is right or wrong. This one you're just used to seeing this one as a student, so it makes it maybe a little bit easier. If it doesn't, then you can just leave it r20. Just realize that those two are being multiplied together, and that's fine. All right, so now what we're going to do is I've got this ln 1.6824. I need to plug that into my calculator to reduce it. Okay, so I plug that amount into my calculator, I end up with this. Now then, all I'm going to need to do is solve for r. So I got to divide both sides by 20. I find out that r is 0.026. Now it asked me to round it to the nearest thousandth, which is 3 decimals, so that's perfect there. Now let's go back over here. Okay, so this is my function, if you will, my formula that I use. And I just plug in what I know. N of t I won't know yet. N of O I do know. That is this 290,811. So I do that. E to the RT. R, I just found that right here is my answer for that one. So this would be my function right here. T would be the unknown, and that's what we're asked to solve for. Find a function that models this population T years after 1990. All right. Now that I know that, the next question that I would be asking is if this growth rate continues, what will the population be in 2025? Okay, well if I do that, all I need to do is plug in T. And I'll know what T is. T would be, let's see, that would be 35 years after 1990 would be 2025. I just plug in 35 for T and I can find my answer. All right, but we're going to kind of move on a little bit. Now, this one, we're going to solve it the exact same way as the previous one that we just did. First, we have to find the function. After we find the function, we can find this second portion of the problem. So I'd like you to push pause on the video right now. I'd like you to work it out. After you've obtained your answer, come back and push play. Check your answers here. Okay, should have come up with a rate on this one of 0.11, which is 11%. 0.11, so this would be your function right here. And then in order to, excuse me, to identify what the population would be in the year 2004, now this one's interesting because it's going to be 8 years after 1996. This one is not 1990. That's an error sometimes students make. But it should be 6 years after 1996, and that's where my 8 years after 2000. It should be 8 years after 1996. That's where my 8 comes in here. So we're just plugging in 8 for that one. All right, same process here, except time is measured in hours here, and that's really the only difference. Okay, so I'd like you to work through these two. After you've obtained your answers, you can come back and push play. Check your answers. All right, now let's go on and try some more. How many hours will the population, or will the bacteria double? So we have to know what double means. Double would be twice this amount here. If this is our function here, we can find out what the time would be. All we're going to do is plug in for n of t. We know what that one is. 2 times 8600, which should be 17,200. So 17,200. Plug that in and see if you can identify that. Pause the video now, work out your solution, then come back and push play. Check your answer here. Should be right around 2.6 hours. And again, whenever you're plugging this into the online system, you're just going to write 4.6, and that's it. Now we're going to talk about Newton's law of cooling. There's a lot of these exponential equations that we can use in real life. Okay, now this one's totally new, a little bit different, but not much from what we had, but it is new. Okay, T of T is the temperature at the time, so this is the ending temperature, okay? Surrounding temperature is T of S. That means like in a traditional room, the temperature would be somewhere around 75 degrees, something like that. That's the surrounding temperature, okay? The initial difference between the object and T of S. Okay, so if we had something that was 100 degrees and we put it in a room that was 75 degrees, the initial difference here, that would be like 25. K is going to be a constant. Typically, K will be given to you. Sometimes you do have to find K, though, and T is time. All right, so let's go through this. A cup of coffee has a temperature of 200 degrees. It's placed in a room that has a temperature of 70 degrees. After 10 minutes, the temperature is 150 degrees. So we need to find the model for this one. In other words, we're going to try to solve this one for K. As soon as we can identify K, then we'll have our model. Then after that, we're going to find the temperature of the coffee after 15 minutes. And then we can identify when the coffee will actually hit 100 degrees, when it will cool down to the point where it's 100 degrees. All right. So first, let's find the model. We got to identify what K is. Okay, so here are all the information that we know. All right. First thing that we know is the difference between this D of O, okay, which is the difference between the coffee, which is 200 degrees, and the room temperature, which is 70. So D of O is going to be 130. This is going to be 130 here. Next, what we're going to find out is T is after 10 minutes. That's time. After 10 minutes, it gets to, it reduces down to this 150. Okay, and 150 would then be our T of T. Okay, so, all right. Now what we're going to do is plug in what we know here. So we've got 150 equals 70. 70, remember, is our room temperature. Okay, 70 is our surrounding temperature. 130 is the difference between the surrounding temperature and the initial amount of whatever it is. In this case, it's coffee, 200. So the difference there is going to be 130 times E. E is the number E. K we don't know, and 10 is the time. So we're going to solve this one for K. So again, we're going to work through almost identical process. The only difference is we've got this 70 here. So the very first thing we have to do is get rid of the 70. Then we can divide by 130. Okay, so I'm going to subtract 70 from both sides. That gives me 80 over here. That wipes out my 70 here. Next, what we're going to do is try to get this E raised to the negative 10K all by itself. Now, you notice that I switched the spot of the 10 and the K. Some students don't like that. If you want to, you can just keep it as negative K10. That's fine. Either way is okay with me. All right, from here, what we're going to do is divide both sides by 130. I divide both sides by 130, and I get this decimal, 0.615385. Okay, we're going to have to round this eventually, but not yet. So that's why I like to have a lot of decimals there. Now what I need to do is I need to get this out from the exponent. So the way we do that is we'll take the logarithm of both sides. But again, I'm going to take the natural log of both sides, because when I take the natural log of both sides, my ln and my e will cancel each other. All right, leaving me with just a negative 10k. All right, so now I've got this, but I don't know what this is, so I need to plug this into the calculator. So I'm going to take and plug in the left-hand side, this number, ln 0.615385, all into the calculator. And that will give me a decimal here. It gives me a negative number. What I do here is I need to just solve it for k. So I'm going to divide both sides by negative 10. Now I found out what my k value is. Well, this is helpful. Now that I identify what my k value is, I can come up with this equation here, this function, and determine, I can leave it t as the unknown, which is what we're trying to do. So if we do that, I plug in everything that I know. 70, I know that's the surrounding temperature, right here, surrounding temperature. 130 is the difference between the surrounding temperature and the initial temperature of whatever the object is. E raised to the negative, and k, now notice up here, k, I got my answer here and it's positive, but notice we have the negative up here, so that's where the negative's coming in. Negative 0.04855 t. This is my function. This will tell me what my coffee can be after any amount of minutes. I can just plug in the number of minutes here for t and then find this out, which is what the next one is. We have to find the temperature of the coffee after 15 minutes. Okay, after 15 minutes, all we're going to do here is just plug in 15 for t. So I take this and I rewrite it, only I plug in 15 for t. And I plug that into my calculator exactly like I see it here, 70 plus 130 times e raised to the negative 0.04855 times 15. If you're using a TI-84 and 83, make sure you're using parentheses around these right here, okay? All right, we do that, we end up with 133 degrees is what the coffee will be after 15 minutes. All right, now when will the coffee reach 100 degrees? So we're going to solve this one for T now. But we know the ending temperature, this time it's not going to be 150 because it's going to be 100 and we're trying to find out how long it's going to take. So we're going to plug in 100 for that, and now all we have to do is solve this one for T. So again, I'm going to use the same process that we did before. I'm going to subtract 70 from both sides. That gives me 30. Next thing I need to do is get this e raised to this exponent all by itself. So I'm going to divide both sides by 130. Now that I've got that, I've got to get all this out from the exponent here so I can solve it for t. In order to do that, I have to take the logarithm of both sides, and the natural log will help to cancel that e out. So I take the natural log of both sides. Now this ln and this e will cancel each other, leaving me with just this, whatever this is. In this case, it's negative 0.04855 t. All right, now that we have that, we need to solve it for t, but I can't do that because I've got this ln here. So I'm going to have to plug this left side here into my calculator. Plug it into my calculator, I find out that I have another negative number here. Notice this asks me to round it to the nearest tenth, but I'm not rounding yet. I don't round to the very, very end. All right, I've got to solve it for t, so I'm going to divide both sides by that negative 0.04855. I do that now, I end up with 30.2. So the amount of time it's going to take is 30.2 minutes. And again, whenever you're typing this in online, you're just going to write 30.2. Okay, the computer's reading your answer there. So, okay, so that's a lot of work, but this will help us. Then we can calculate what the temperature of the coffee is going to be at any time, and we don't have any restrictions there. Okay, the human body. Okay, it's normally 98.6. And this is how they use it whenever they're trying to do like a crime scene. The dead body is found in the woods where the temperature of the woods is 30 degrees. The constant for the situation would be 0.1, so that's given to you. Write an equation that models the temperature as a function of T. So we plug in what we know. Okay, so this is Newton's law of cooling. We know T of S. T of S is the surrounding temperature. That's going to be 30. Okay, now we can identify what D of O is. Okay, that's our initial difference. So we take our 98.6, subtract our 30, that gives us 68.6. So my D of O in this case is going to be 68.6. 98.6 is the body temperature, this is your surrounding temperature. We calculate the difference between those two. All right, now I know what K is because that's 0.1 that was given to me. The constant for the situation is 0.1. That is my function. Now we're going to use that to determine what temperature the body would be after 3 hours. So you work on that now. Push pause on the video now. Figure out what the temperature of the body would be after 3 hours, and then come back and push play. All right, so we're going to work through this one. All we're really going to do is plug in 3 for T. That's it. We find out that the temperature is 80 degrees. 80.82 would be the temperature of the body at the time. This is what police used to determine when the time of death was. If the body was found and it was 40 degrees Fahrenheit, how long has the person been dead? Then we need to round our answer there. Okay, so we have our model. This is our original model. Now, we just know T of T at this point. We're going to plug in 40. So I'm going to let you do that one. Go ahead and push pause on the video now. You should be able to do that at this point. Try to work that out and see how long the person's been dead. When you've obtained your answer, come back and push play. All right, we're plugging in 40 for T of T. I'm going to kind of walk you through this one just in case you struggled on it. I'm going to subtract 30 from both sides. Now then I need to get this portion right here all by itself, so I'm going to divide both sides by 68.6. That gives me a decimal over here. And that's perfect so far. Now that we've done that, I need to isolate this. I need to get this out from the exponent. The way I do that is take the natural log of both sides. And when I take the natural log of both sides, this ln and e will cancel each other, leaving me with just this exponent. All right. Now I plug the left-hand side here over here into my calculator. That reduces it down just a little bit further, and I can divide by 0.1. This will give me the t. 19.26 hours is how long that person has been dead. So you can see this, it's a lot of work on these, but you can really calculate very precisely anything from how much money you're going to have in 20 years from now or 40 years from now, how much you want for retirement. You can back that off and see how much you need to start putting away right now. You can find out how warm something is, when it's cooling off, how long it's been there, sitting on the counter, that type of stuff if you wanted to. Hopefully this worked for you. You may need to go back in and watch this one a couple times. This is a very real-life intensive lesson. A lot to it, but hopefully it made a little bit more sense by the end.